Oh well, let's get started. Good enough. Okay, last time we, it's good enough. We introduced the last of our rules for logical derivation, our rules of derivation, the ones dealing with the existential quantifier, right? And that's kind of where we ended last time. And then we talked a little bit. Oh, actually, it was Levi posted that video. I don't know, did any of you guys watch that video that he posted? It is a fantastic video. You should definitely go back and watch it.
Is it on Facebook?
Yeah, on Facebook, on the class page. Yeah, he posted a video. I don't think it was that long, like 40 minutes, something like that. Not that long compared to one of these lectures, but the guy does a phenomenal job laying out some intuitions for how logic lays at the foundations of mathematics, introducing undecidability. So for those of us who just came out of computation theory, he also ties computation theory into this and talks about how we use the concept of undecidability relative to math things. So one of the things Gödel showed is that, not Gödel, losing a bunch of names. The guy who taught Alan Turing. Alonzo Church, there we go. One of the things Alonzo Church showed is that the reason that we can't just derive things from logic is it ends up being undecidable. So that video does a phenomenal job introducing undecidability into it and then introducing the concept of Gödel's incompleteness theorem. What did Gödel show? Gödel showed that there's some things out there that we know are true that provably we can't prove them to be true. So we know they're true. How do we know they're true? Because we can't prove that they're true. So how do we know that they're true? Through this thing called human understanding. And so what that shows is that human understanding, whatever it is, it can't be encoded in some axiomatic system, which is mind-boggling. Because every theoretical body of knowledge we have is an axiomatic system. So you might have some notion of, well, see, everything that goes on in the brain, that's just biology, and everything in biology is really just complex chemistry, and everything that's chemistry is really just complex physics. And physics, that's just applied mathematics, and mathematics can be captured in axiomatic systems. Human understanding happens in the brain, so yeah, you should be able to develop an axiomatic system that encodes human understanding. No, you can't, provably. Weird. Very unintuitive. And to give you some intuition, he gave a perfect statement that captures, it's just an analogy, but it captures exactly what Gödel showed. So Gödel showed that there's a statement like this statement. This statement cannot be proven true. Now, is this statement true or false? Well, if the statement's false, then it could be proven true. So then it's true. So if it's false, then it's true. So the statement can't be false. So it is true. Hence, what does the statement say? That it can't be proven true. And so that's what Gödel does. He demonstrates that there's this kind of statement. This is just an analogy. This isn't the actual statement. But that there's this kind of statement in arithmetic. And in fact, there's infinitely many of them. Because if you then said, okay, so we couldn't prove that statement in arithmetic, let's introduce that as an axiom. But then you can reapply his method to find another statement that's just like that. And again and again and again. And so you can introduce infinitely many axioms, not infinitely many. You can introduce any large number of axioms you want, and there would still be true things in your system that you cannot prove in your system. It's crazy. So it's a great video. Does a phenomenal job trying to give you intuition for this kind of thing. Lots of nice animations. He has a nice organized script that he thought out so that he's not forgetting stuff on the fly. Strongly recommend watching it. It's a great video. Does way better touching on those concepts than I did last time. So, moving on to today's material. The first thing we're covering today is the interchange of quantifiers. Now, the author just states, hey, we can interchange quantifiers like this. We're going to prove it later. So this isn't a rule of logic. This is not a rule of derivation. This is something that we're going to prove later. We're just going to use it now.
Why not spirit right now?
Because we haven't gotten to theorems of logic yet. which we'll get to.
So it's just immediate.
It's going to be a theorem of logic. But yeah, let's just start using it now. Because it's easy enough to just grasp it with your intuition.
Okay.
So we will prove this to be the case. We have not yet proved it to be the case. This is not a rule of logical inference. This isn't a rule of derivations. This is something that we say, we're going to show that we can do this later. We're going to start doing it before we prove we can do it, basically. All right, so what does it say? The two ways we can switch out quantifiers. The first one says, if x is any variable, and if formula S results from formula R, by replacing an occurrence of for all x by it is not the case that there exists x such that not whatever it is, then S is derivable from R and conversely. Seems like a mouthful. Once you see it, I think the mouthful will make perfect sense again. What's he saying? He's saying, here's the R up there, here's the S up there. If you know that for all x, some predicate about x is true, if it's the case that for all flowers, a flower is red, that's identical to saying it is not the case that there exists a flower that's not red. If all flowers are red, then it is not the case that there exists a non-red flower. That's what this is saying. So here's the R, here's the S. We take R and we substitute the for all x in R with not there exists not in S. That's what it says we can do, and conversely, I can replace that with a for all. Good? Pretty straightforward? All right, let's do an example of that, just to make sure it's as clear can be, and then we'll go from there. So every mathematician admires Archimedes. How might we write that? Let's get used to formalizing these sentences again as well. What should I write?
For all x.
For all x.
AX.
AX? What does AX mean?
Means that they admire Archimedes.
Okay.
X admires Archimedes.
X admires Archimedes.
NX implies AX, like if they're a mathematician, then they like Archimedes.
That's the way I would say it.
Okay.
If
If
mathematician
X
applies to X, then Archimedes applies to X.
Yeah.
All right, wonderful. Now let's read what this one's saying. It is not the case that there is a mathematician who does not admire Archimedes. How might we write that one?
Not there exists.
Not there exists.
I guess you just say not on the outside of that parenthesis.
All right, so we'll do not, and then we'll do inner parentheses.
You do NX implies AX, right?
Not, well, let's read what this says. It is not the case, well, where are we? It is not the case that there is a mathematician who does not admire Archimedes. So we're saying it is not the case that there exists someone who is both a mathematician and they don't admire Archimedes.
So NX implies not AX?
No implies, it's an and.
Oh, yeah.
They're a mathematician, and it is not the case that they admire Archimedes. So we didn't really need the square brackets, but there we go.
Okay.
Everyone agree that that's the form of this sentence? All right, now using this rule, I'm going to show you that this gets us to this. Maybe we should have said this. This is what we were supposed to do. We're supposed to intuitively see that these are both saying the same thing, and then use a rule to connect these two forms. That's what the point of the exercise is. So I'll make sure that we intuitively understand that these are saying the same thing. Every mathematician admires Archimedes. It is not the case that there is a mathematician who does not admire Archimedes. You can't find one who doesn't. So they all do. Okay. Now let's show that these two forms are the same using this rule. So I'll start by this with this one because it's the simpler of the two. Let me apply this rule. So first I'm going to take this, I'm going to replace the for all with a not there exists, and then I'm going to not the whole thing inside of here. You with me?
Mm-hmm.
So this is logically equivalent to not there exists x such that not m of x implies a of x. And now not Emma, tell me what we should do with this.
That's equivalent to some kind of and statement, if I remember.
Probably.
I remember this. I just remember what it is.
What's an equivalent form of alpha implies beta?
Contrapositive.
Not alpha or beta.
What? Not alpha or beta.
That's what it was.
Not alpha. Was that a guess or did it make sense to you?
No, I mean,
Yep, what?
it came back to me.
If you know that if I'm wearing shoes, then I'm wearing socks, you know one of two things. Either I'm not wearing shoes or I am wearing socks.
Yeah. Yep.
Make sense? So that's the substitution we're going to do to the implication arrow there. So I'm going to replace that implies that with not alpha or beta. And then we know how to distribute a not over an or. Distributing it over an and we're not, or distributing it over an implication we're not as used to. So we'll switch it to an or first. So this is the same thing as not. Let me just switch it in here because we're going to run out of space. So mx implies ax is the same thing as not mx or ax. Not mx or ax. Right? Okay, now we remember how to distribute a not over an or?
Make it an and.
Yeah, you make it an and. If it's not alpha or beta, that's the same thing as not alpha and not beta.
Yep.
If I don't have a car or a house, then if it's not the case, I have a car or a house, then I don't have a car and I don't have a house. Alright, so that's what we're going to do. Distribute the not through those. And so we get not, there exists, not mx is just the same thing as mx. Switch the or to an and then not ax. There does not exist a mathematician who doesn't admire Archimedes. There doesn't exist anyone who's a mathematician and they don't admire Archimedes. Exactly what we were trying to show. Ta-da! The rule worked. Okay. Second rule, very similar. If x is any variable and if formula S results from formula R by replacing a occurrence of there exists x by not for all x not, then S is derivable from R, and conversely. Pictorially, what's that saying? That's saying we can take the there exists x and replace it with the not for all not p of x. Again, let's get intuition for this from the sentence, and then we'll write them out here. If I tell you that there is a two-headed calf, what am I telling you? I'm telling you that it is not the case that it is not the case that no calves are two-headed. If there is a two-headed calf, then it's not the case that no calves are two-headed. Yeah, when we convert it, we get a double negative in there. So always sounds a little funny. So let's write those ones out, see how they're connected, and then go on our merry way. All right, first sentence. There is a two-headed calf. How do we write that?
There exists x.
There exists x
T opposed to x.
such that two-headedness applies to x,
Yeah.
No.
Calf.
and being a calf applies to x. And being a calf applies to x. There's something out there that's two-headed and a calf. Wonderful. And where are we trying to get?
Not for all x.
Trying to get not for all x.
And then maybe not. And then an implication.
It is not the case. Sorry, where do we start? We start right here. It is not the case that no calves are two-headed.
So if calf applies to x, then two-headedness does not apply to x. So not two-headedness applies to x.
Not for all x. If it's a calf applies to x, then not two-headedness applies to x.
Yeah.
You like that? There exists x such that it's two-headed in a calf is the same thing as it is not the case that for all x, if it's a calf, it's not two-headed.
Yeah.
Cool. Now let's connect those using this rule. So the rule tells us that I can replace the there exists with a not for all x, not t of x and c of x. So that's just using the rule exactly. The rule says I can replace the there exists with the not for all not. Okay. Then we distribute the not over an and, converting it to ors. So this is the same thing as not for all x. We have not t of x or not c of x. Let me swap the order of those because we have them swapped down here where we're trying to go. Or is, how do I know I can swap those?
It's associative.
Commutative. We already showed or was commutative. Alpha or beta is identical to beta or alpha. So I'm going to swap the order I write those. So not c of x or not t of x, right?
Yeah.
Now I want to convert that to an implication. Go the other way here. I know that not alpha or beta is the same thing as alpha implies beta. If I want to switch it to an implication, I just need to negate the first thing. Right? So if I want to switch this to an implication, I just need to negate the first thing. Which is exactly what we have right there. So then that's logically equivalent to that. Yay, the rule worked. Ooh, who saw that coming? Okay. So those are those two rules for interchanging quantifiers. We did that, we did that, we did that. No. Some books just define the existential quantifier as there exists x such that p of x. They just define it in terms of the universal quantifier. So they define there exists x such that p of x. They define that to be not for all x, not p of x. We instead are going to prove that that's a rule from that. We're going to prove that that's true from our rules. So some people just have the rules for universal quantifiers and then introduce this as a definition. Our author instead had rules for universal quantifiers and rules for existential quantifiers. And it turns out that our rules for existential quantifiers are going to make so that we can prove that this is the case. So logically equivalent ways of coming at it. You can have just the rules for universal quantifiers and define it this way. Or you can have your rules for universal quantifiers and existential quantifiers and prove that this is still the case. The more modern way, I think, now is to just define it this way. But same thing. Okay. Another rule that the author proves, they actually proved in this section that we can use it. We won't bother with the proof. It's pretty intuitive that we can do this, and we've already been doing it because not doing it makes proofs take way too long. But the author writes out all the proofs that we do in like 10 lines. He takes the full 15 lines in the book to do. So what does rule TE allow us to do? That's a rule of tautological equivalence. In short, here's what it's going to say what you can do. It's going to say if you've got a formula, you can replace a piece of the formula with something that's tautologically equivalent to it. That's what it's going to say we can do, and we've already been doing that.
Yeah.
And how would you prove that you could go from this to this? You'd universally specify, which would give you that formula, then use a rule that we have, rule T, to get that, then universally generalize again. And you say, that's a lot of steps, let's break that down to one step that we'll call TE. I pretend it's still just T. When we use this rule going forward, I'll still just call it rule T. But he decides to prove it explicitly because now he's tired as the author of not being able to do what we've been doing. So what's the rule? If P is a part of some formula, here's P. If P is a part of some formula R, and Q is logically equivalent to P, and S results from R by replacing P with Q, then we may derive S from R. Make sense?
Yep.
In other words, you can swap out tautologically equivalent pieces with tautologically equivalent pieces. Perfectly valid. Okay. Now, proof here, where in the proof we're going to have to use some of our swapping out rules that we have over there. So, Let's do it. If there's a federal court that will sustain the decision, then every member of the bar is wrong. How are we going to write that one? If there's a federal court that will sustain the decision, then every member of the bar is wrong.
So there exists X
There exists X
such that decision applies to X, or
sustaining the decision applies to X.
yeah.
Okay.
Well, they also have to be a federal court.
And they also have to be a federal court. So we'll say being a federal court applies to X. And sustaining the decision applies to X.
Wouldn't we say for all X then?
For all X,
No.
that's a better choice.
What?
Now,
Saying
if there is something that's a federal court and sustains the decision,
that
but you're
implies-
thinking about wrapping it. I don't know. Depending on where he's going with this, could be good.
Okay.
And depending on what you were after, could also be good.
that implies,
So you're saying in the parenthesis here, right?
yeah,
Okay. And that whole thing implies, okay, then we'll be good.
yeah. For all X.
Let's swap our variable. Say for all Y.
Yeah, either one. Being a member applies to Y, so bar applies to Y or something.
Being a member of the bar applies to Y.
Implies,
Well, and they're wrong.
it implies that they're wrong,
It
but
implies that being wrong applies to Y.
yeah.
Being wrong applies to Y. Perfect. I think that's perfectly valid. And I didn't leave myself space to write the numbers here. Oh, premise one. So, first premise. If there exists something such that it's a federal court and it sustains the decision, then for all Y, if Y is a member of the bar, they're wrong. That's right.
Okay.
At least I think it's right. Alright.
Just based on the rest of the sentences, should we write wrong is not R applies to Y or something? Like not right?
You can do wrong, or you can do not right.
Okay.
It doesn't matter which way we do it. This was a premise, and there were no free variables in there, right?
Yeah.
And it just depended upon itself for its validity. Okay, what's our next premise?
Some members of the bar are right, so
There exists.
there exists a Z, I guess, where
Sure.
not wrong applies to Z.
Why would you just use Y?
Well, member applies to Z and, so bar applies to Z and.
Z's look cooler.
So
Isn't it supposed to be the same Y though?
Logically, they're connected. So I'm okay with using a Y there. But that's you reading meaning into the forms of the things, right?
It doesn't really matter all the way through. I mean, we
No,
could,
it doesn't matter.
we
but
could use X's all the
I
way
like
if we
his
wanted
choice
to,
of
right?
using Y. Showing that they're connected. I would have used a Y.
So bar applies to Y and not W applies to Y.
Bar applies to Y and not W applies to Y. There exists something that's a member of the bar and they're not wrong. Not the premise, only depend upon itself. Okay? Therefore, no federal court will sustain the decision. Oh, that's what we're trying to show.
Yeah,
Maybe let's just write what we're trying to show to the side. Sometimes that helps us not make mistakes.
that'd be good.
So what are we trying to prove?
There exists X.
We're trying to prove there exists X.
Oh, no.
Oh, no.
It's for all X, sorry.
We're trying to prove that for all X.
Sustain the decision, well, FX
Being a federal court applying to X
and not SX.
Implies.
and not sustain the decision
Or
applies
is
to
it-
X.
Is it implies?
And then
I
just
think
put
it's
a not
implies,
there.
because that just means all X's are federal and don't sustain.
No,
What
that
you
would
want
be a
is the
direct
implies.
contradiction of what we have known.
What you want is the implies.
I think.
It looks like it does. Why don't you just put not up there?
If it's a federal court, then it won't
Yeah, if you're
sustain.
federal court, you will not sustain.
Yeah, that-
Not X. Yes, that's the way I like it.
Okay.
For all x, if it's federal court, it will not sustain the decision.
Okay.
What is the domain here?
The domain here,
On
you
X?
can think about the federal court as being a federal judge and call people.
So, so X could be any person if they're a judge then.
Yeah, you can think about x as being a person, and federal court just means a judge, federal judge. Okay, so that's what we're trying to get to. All right, so what should we do now?
Imagine you're gonna have to use the rule that we just came up with somewhere in
Somewhere in there, and we kind of only got like one thing to do it to.
there. The first one, probably.
No, I think the first one.
You could substitute, we have the for all y on that first line, you could do that substitution for there exists, like the not there exists, not be one.
You're saying on this one?
And then, yeah, and then use the contrapositive of one. So if you switch that for there exists and then use the contrapositive so it's the first, then at least we can use line 2 to prove
Oh,
something.
yeah, we'll be getting to that. I see what you're saying. And then you get the implication from this.
Yeah.
Let's get the implication from this first. I think that makes better order.
Okay.
You got the right idea. That's exactly what we're going to do. I just think messing with this will be easier to see. So we're going to start with this, and we're going to apply the rule to this. Not for all not. We're not even going to think about anything yet. We're just going to blindly apply the rule. All right? So, not for all y. And now we need to negate this thing, right? So,
Not B or W.
I'm not sure how much to do all in one go.
Not BY or not. Yes, W.
We'll stick with it like this for a second and then factor out the not. Well, are you okay with me going straight to this?
Yeah.
Or WY?
Yep.
So I just barely distributed a not over that, switching it to an or.
Yeah.
So we have not that or not that. Okay. Maybe I shouldn't have been so worried about doing that all in one go. Okay. So I'm kind of slanting those. This right here is tautologically equivalent to 2, right? And so this is still just dependent upon premise 2 for its validity. Okay, now let's rework this as an implication.
So
Not for all y.
BY
Implies
implies
W.
not implies WY.
Remember, let's just write this side over here again really quick. Alpha implies beta is the same thing as not alpha or beta.
Yeah.
So if you want to switch an or to an implies, just negate the first thing.
Yep.
So we're going to switch an or to an implies by negating the first thing. And so we get by implies wy, right? Again, that's tautologically equivalent to 3. Still our only premise that depends upon is 2. And now, contrapositive. Notice that this is the negation of this.
Yep.
So, alpha implies beta is the same thing as not beta implies not alpha.
Yep.
So now we can use this and this to get the negation of this. So, let me know if anyone doesn't follow how I got not this thing. Not there exists x, such that f of x and s of x. Everyone good with where that came from? Using contrapositive? You see a contrapositive?
Where'd your first bit go? Where's your implies?
Wonderful. Alright, so alpha implies beta
Yeah.
is the same thing as not beta implies not alpha.
Yeah.
So if I know not beta implies not alpha, and I know not beta, put those two things together, and I get not alpha.
Oh yeah.
That's what we did. So, not alpha. And this was tautologically implied by lines 1 and 4. And now we're dependent upon premises 1 and 2 for our validity. Alright, now what? Here's what we were trying to get. So let's just swap out the existential quantifier with the universal quantifier again.
Yep.
How do we do it? Not for all not. So not gives us nothing. So not, and then we have for all x, and now we gotta negate what's inside of here. Again, I'm just gonna distribute the not through it as we go.
Okay.
And just say that's not fx or not sx. Good with that?
Yep.
And then finally, line 7, turn a or into an implication, you just negate the antecedent. That's the same thing as for all x, fx implies not sx. Ta-da! So this line was tautologically equivalent to line 5. This line was tautologically equivalent to line 6. We're using premises 1 and 2. We're using premises 1 and 2. And so when it was all said and done, we only used the two things we were supposed to use as premises to prove that. And we're good. Good?
Yeah.
And a nice proof throwing us back into everything we talked about last time, using those quantifiers. Okay. Now, the next section in the book, the author talks about some restrictions to the rules that we already have. Now, almost all the restrictions we talk about here never naturally come up. So you can almost ignore this section. No one naturally tries to do these things hardly ever. But these restrictions are out there. So these are things that we didn't explicitly state in the rules when we came across them the first time, but they're restrictions and you can't do these things. Alright, so what are the restrictions? Restriction number 1. We cannot existentially generalize to a free variable in the formula. What do we mean by that? So let's start with the statement that, giving it an arithmetic interpretation for all these, that we can see that this is true. For all x, there exists a y such that x is less than y. What are we saying? There's no largest number. Pick any number you want, I can always find one bigger. You played this game as a kid, right? First thing we do, universally generalize on the x. Okay, then we get this, perfectly valid. Next thing we do, we existentially generalize, or sorry, that was universal specification. Now we're going to do existential specification on the y. X is less than alpha, still good. Now I'm going to cheat, and I'm going to existentially generalize to a free variable in my equation. X is a free variable, I'm going to existentially generalize replacing alpha with x. I get there exists x such that x is less than x. Can't do that. Intuitively, you have never tried to do that, but there's a rule that says you can. So going from here to here is where we cheated. Up till there we were fine.
Why would you theoretically be able to do that using the rule that we have?
Our rule, so far, we didn't have a rule that said you couldn't do this. Our rules allowed you to do that. Our rules just say you can do these things. And so there's some restrictions on our rule that we technically should have specified when we gave the rule, but it was just too much to swallow all in one go.
I didn't realize that our rule even allowed us to do something like that.
Yeah, the rule for existential generalization, it didn't say, as long as it's not a free variable in the formula, you can do this.
But it did for universal, right?
For universal specification,
For universal generalization.
universal generalization said it can't be a,
Free variable.
Flag.
not a free
Flag
variable, a
variable.
flag variable. Very different. It's always a free variable.
Yeah.
Yeah. Alright, second restriction.
It's always a free variable.
Yeah, you universally generalize free variables.
Oh, yeah.
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 Okay, next restriction. This restriction is on universal generalization. We cannot universally generalize free variables prior to existential generalization. This allows us to swap the orders on our quantifiers, which then makes true statements false. So let's see that in action. This says for all x, there exists a y such that x is less than y, which is good. It's true. Ultimately, where we're going to get is what's false. There does not exist some y such that for any x you choose, it's bigger than that x. That's what you would say if you swap the quantifiers. So here's our true statement. We're going to get to a false statement, breaking the rules. You with me? Is it appealing to everyone's intuition how this is true and this is false?
No.
This one right here says for any x you choose,
Yeah.
there exists a y such that your x is smaller than the y. This says you pick any x you want, I can find a y such that it's bigger than your x. This one says you can find a y such that for any x I choose, my x will be smaller than your y. You know of some magic y such that for any x I choose, my x will be smaller than your y. Now, there is no magic y you can come up with that's bigger than every other number. Okay, so that's what it's going to enable us to do, which is a cheat. Let's see a cheat in action. Universal specification on x, existential specification on y. Now, the cheat, we're universally generalizing. We're saying for all x, x is less than alpha. And then existential, here to here is not cheat. That's just doing the existential generalization. So we can't go from x is less than alpha to every x is less than alpha. That's our cheat. Make sense? Okay, next one. We cannot universally specify to a bounded term. If you do universal specification, you got to pick a variable that's not already bounded by the equation some other way. So if I know that for all x, there exists a y such that x is less than y, I cannot then universally specify on x and replace it with y. And say, oh, there exists a y such that y is less than y.
Oh, yeah.
Okay, last one. We cannot existentially generalize to a bounded variable. I don't know why I switched the example on this, but I guess I did. Okay. There exists an x such that for all y, x plus y equals 0. Equals y. And what's the x? The x is 0.
Yeah.
There exists an x, namely 0, such that for all y, x plus y is equal to y. So it's a true statement. All right. Universal specification. Then you can say for some alpha, then for all y, alpha plus y is equal to y.
True.
Here's a cheat now. We existentially generalize to an already bound variable, namely y. To there exists a y such that for all y, y plus y is equal to y.
Sometimes.
And now we're not even sure how to interpret that thing.
Yeah.
What's that saying?
0, 0.
0.
Yeah, but for all y, there exists y such that for all y. Yeah.
Right. So it gets us into a weird state where we're not sure what to do with it. We don't want to try and interpret what that weird sentence means, so we just say, there's a rule that says you can't do it. Okay, now we don't have to worry about what that means. All right, and then here's an example that has nothing to do with the restrictions, but the author puts it in as an example, so we'll do it.
Yeah.
He put in, I think he had a historical note about there was some logician who thought that this statement couldn't be proved from the rules of logic that we have, and then someone proved him wrong proving it. So we're going to prove a statement that a logician at one point thought couldn't be proved.
Wrong or right?
He thought you couldn't prove this. You can't go from this to this. We're going to do it.
Okay.
All right. All horses are animals. Therefore, all heads of horses are heads of animals.
Why did you not prove that?
Because it's weird, because it introduces the heads in there. We can't prove it. It's just, he introduces like some historical note that some guy thought you couldn't for some reason.
Fun fact.
Yeah, just a fun fact about this one, so. Where should we start? Let's start by writing out our premise. We know what we know. What's the first one?
For all x, h applying to x implies a applies to x. Yeah.
For all x, if being a horse applies to x, then being an animal applies to x.
True.
Now, the whole hard part of this proof, that's our premise.
Do you have to do a conditional premise?
Right. Let's understand what we're trying to prove first, and then you'll understand how to do the proof, I think. What are we trying to prove? Therefore, all heads of horses are heads of animals. Let's write that statement. All heads of horses are heads of animals.
If something is the head of a horse, then it's the head of an animal, right?
How do we write that?
For all x.
So
We'll write that down over here. I'm not sure how much space we need. Can't remember. There's a
maybe
big
for all
proof.
y, just so we have a variable.
For all y, what are we saying?
Head applies to y, whatever you want to use for
Being a top applies to y.
implies that. Oh, wait a minute here.
Yeah, where did that come
Head of being ahead of a horse.
Being ahead of a horseness applies to, being ahead of a horse applies to y.
Being ahead and being part part of a horse.
Why, or,
Well, we can't have our head be a horse. We know that that's not going to work.
Yeah.
So we can't say horseness applies to y.
you say G applies to H of Y?
So let's start with for all horses. So we'll start with an x. We're trying to show that for all horses, well, for all x. Then what are we trying to say? We're trying to say if it's a horse and it has a head, then it's an animal that has a head.
Okay, so horse applies to X and that applies to X. No, well, yeah, you're running the
If
same
there
problem.
exists a y such that horse applies to x and y is the top of x, we'll write like that,
Yeah, yeah.
implies what?
Applies animal. I feel like I'm missing the quantifiers.
Implies there must exist a head, there must exist something where animal applies to x and being the head of x applies to y. There has to exist some y such that y is the top of x and x is an animal. Probably should have swapped the order on those. Being the top of meaning it's the head. You just can't use
for
h
all
because
X
we did that for horse.
outside of that entire.
And for all x is outside the whole thing. For every x, if there exists a y such that y is the head of x and x is a horse, then there exists y such that y is the head of x and x is an animal.
Okay, yeah.
So that's what we're trying to get.
Okay.
Okay. So here's what we're trying to prove. How might we prove that statement?
We'd have to have a conditional premise that
Can start out with a conditional premise. So
that
two,
does in fact exist ahead of us.
assume the antecedent, show that implies a conclusion.
Yeah.
So assume the antecedent.
There exists horse.
Oh,
You're gonna have to, can you distribute your,
Yeah, what's the antecedent?
what do you do about that?
yeah, we're gonna introduce the antecedent just being this piece.
And then you're gonna generalize the answer.
Show that implies this piece. It's the same way we always do it. When I tell you that, did we not prove any implications up here? It's the same way we did it going back to, I'm trying to think of a simple example off the top of my head. We do this all the time though. When it's a for all, when we say the antecedent, we still just mean this piece.
Yeah.
We always have our implications bounded somehow.
Can
I'm
you,
still, oh, sorry, I'm still just a little bit confused on what we're trying to get to. It seems like it's saying that if the horse has a head, then it's an animal that also has a head. But like, therefore all heads of horses are heads of animals. Somehow like, it's like.
Maybe I wrote the statement
making
down a
them
little bit
equal to
weird.
each other. Like the two heads.
Let me see. There's a two-headed calf. No. Let's go back to here. Therefore,
Like what we're trying to prove would be the same thing if our second set of y's were z's, and then maybe my point would come across better. Because it's like, it's a whole different head, even though it's like not realistically.
all horses are animals, therefore all heads of horses are heads of animals. Is that how I wrote it? Okay, we got that right. Okay, so for all x, if there exists something that is the head of x and x is a horse, then there exists something that is the head of x and x is an animal. Being the same thing, the same x.
Yeah, the x's are the same, but the y's don't have to be in this situation.
you can think about this whole thing as being X has a head as a horse implies X has a head as an animal.
Okay. So the Y's they don't like have to be the same.
My gut says I could pull the whole Y out and it doesn't change anything. Maybe it does. I actually kind of see what you're saying. Let me see how the author encodes a sentence. Oh, he used P for horse. And then headed. Here, all the same way we did. But I like your point there.
It makes sense mostly. It's just the fact that the heads, like your sentence says, all heads of horses are heads of animals, and this is like, if it has a head, it also has a
Yeah,
head as an
therefore, it's like we're assuming that if it has a head, it only has one head.
animal. Right. True.
And we're using that as an assumption there. So what's the way we could have written this to be slightly more specific? Therefore, all horses with heads are animals with heads.
Wait a minute. It might not be a problem because all you're saying is if it's a horse head, then it's an animal head. I'm not saying anything about the other heads the animal might have.
Here, I think she's right in what she's saying. For all X, if there exists something that is the head of X and X is a horse, then there exists something that is the head of Y, or is the head of X and X is an animal. Now maybe our horse has two heads. And this could have been talking about the first thing being the head of the horse, and this could have been talking about the other thing being the head of the animal. In which case it's not the same
It
head.
might not be referring to the same thing.
Yeah. The Y here might not necessarily be referring to the same thing as the Y here. Now it's natural for us to think it's referring to the same thing because it only ever has one head. And so we could have worded this a little bit better to say, therefore, all horses with heads are animals with heads.
Right.
So we'll pretend that that's what we're proving, because I think that's a valid
Okay,
point.
yeah, I just wanted to be sure.
Right.
All right. Okay, so here's what we're trying to prove. So, assume the antecedent, show that until the conclusion. Right? So, write out our antecedent. Our antecedent is there exists Y such that Y is the top of X. I'm going to swap the order because I think it reads a little bit better. And X is a horse. This is now a premise, premise 2. And notice that in here, X is a free variable. Or not a free variable. It is free, but it's a flagged variable. Okay, so now what?
Do you introduce that as a premise or as a conditional premise?
Conditional premise, which is why it's indented.
Do you not write CP?
No, CP is the rule. I accidentally kept saying conditional premise. CP is a rule of conditional proof. It's the rule for removing a premise.
So
This is rule P. Rule P is you can introduce anything you want as a premise at any point. Go for it.
So when we're done, we'll remove it.
This will no longer be a premise, and we'll use conditional proof to get rid of that.
A flag variable has no quantifiers applied to it, right?
Yes, a flagged variable is a free variable in a premise.
Free variable on a premise.
Correct. Okay. All right, so we got that. We're trying to get from here to here. What are we going to do next?
Where are you going to get the A from? You're going to have to use your first.
Yeah, you're going to have to use your. We're going to have to use our only premise.
Sorry, just-
You can universally specify on
Universally specify on this. I existentially specify on this first, and then universally specify this to the same variable.
Okay.
So let's existentially specify on this. If there exists a Y, such that Y is a head of X and X is a horse, then we'll call that Y something, we'll call it beta. I'd say alpha, but my alphas look too much like X's. So then we know that there's some beta such that beta is the top of x and horse applies to x, right? And now we can universally specify on this, replacing our x's with betas. Right?
I mean, we can.
Did I do something weird?
Why
I'm
would
just-
we want an h of?
Oh,
beta
no,
and
sorry.
h of
We're
x?
doing that with that. Yep, I was thinking weird. You're correct. Never mind. We're universally specifying on this with just x's. Correct.
Oh, okay.
So we could have done that first. I was thinking weird. H of x implies a of x. So this was universal, not universal. This was existential specification on line 2. This was universal specification on line 1. This was just dependent upon premise 2. This was just dependent on premise 1. Okay. So now what?
I'm getting a little held up on your flag variables. I'm trying to remember how.
We just can't universally generalize until the flagged variable is gone.
That's the only.
In other words, we need to remove this thing as a premise before we can universally generalize again. You can't just introduce a premise and then universally generalize it.
I'm trying to remember how we think about a flag variable. You treat it like a variable, but you don't know.
Treat it the exact same as a variable. The only rule with flagged variables is you can't universally generalize them.
But you're assuming. Are you assuming that an instance?
It would be like
exists?
in a math proof. So you're trying to prove an even squared is even. You say let x be an even. You cannot conclude from let x be an even to all numbers are even. Because let x be an even, that's going to be a flagged variable there. You say let x be an even, and you show that implies something, and then once you have your implication, you're no longer pretending x is even, and you can use your x variable for something else again.
Okay.
That's the same thing as a flagged variable here. This is the same thing as let x be something, let x be a horse, such that there exists a y where y is ahead of that horse. That's how we'd write it out using informal language. Okay, so now we can combine these two. I know h of x, and I know h of x implies a of x. Put those things together, and I can conclude a of x. So 5 is btx and a of x.
Yeah.
This is tautologically entailed by lines 3 and 4. It's dependent upon 1 and 2, where 2 has a flag variable x. Now what can we do?
Existentially generalize on 5.
Existential generalization. So 6, now we existentially generalize on that, and so we say there exists y such that y is the top of x, and animal applies to x. That was existential generalization on line 5, dependent on premises 1 and 2 with the flag variable. And now we use a rule of conditional proof. So we show this implies this. So now we can say there exists y such that y is the top of x, and being a horse applies to x, implies that there exists y such that y is the top of x, and being an animal applies to x. That's using the rule of conditional proof. Our conditional proof started at 2 and ended at 6. I like to indent where they start and end so I can keep track of it better. And now we're only dependent upon premise 1. We are no longer assuming that that's true. We showed if it's true, then this is true. But we're no longer claiming that this in and of itself is true.
So is that how you get rid of your flag variable?
Yeah, because the rule of conditional proof, the rule of conditional proof says that if I can show, remember that fancy P here just means the conjunction of all my premises. If I can show all my premises together with alpha implies beta, then that's the same thing as just my premises alone implies alpha implies beta. This is alpha, This is beta. This is my premises. I showed my premises and alpha implies beta. Therefore, my premises alone, just one, gives me alpha implies beta. So that's using a row conditional proof. And now there's no flag variable, so now we can universally generalize. And now we can say, okay, then for all x, it must be the case that there exists y, it must be the case that if there exists y such that y is the top of x and x is a horse, then there must exist y such that y is the top of x and x is an animal. Oh, and that, forgot to write the rules here. That was using universal generalization on line 7, and now we're only on premise 1, and so we did it. We showed that this is entailed from just that premise alone. Make sense there?
Can't believe you didn't figure it out.
I'm not sure exactly what the footnote is. You can go read it. You know, read your textbook. Imagine that. I don't remember exactly what it was. I thought we were at a different part in the book today. That's why that stuff's over there. I thought that's where we were, and I was like, oh shoot, oops. That's what comes after this. But it's just why I wrote it in a weird order. Okay, good enough. Okay, couple example proofs, and then we move on to the next section. First one, none of Occam's followers like any realist. That's Occam as in Occam's razor. Any of Occam's followers like at least one of Hobbes' followers. Occam does have followers. Therefore, some of Hobbes' followers are not realists. Huh? Square box? Let's make sense of it. All right, what's our first premise?
If they're a follower of Occam. So basically, for all x,
For all x,
O applies to x,
being a follower of Occam applies to x.
implies. Oh no, I got to y too.
None of Occam's followers like any realists.
You have to say that there also is a realist, right?
Where?
So there'd be a like relation with
Well, you have to put
Occam's
y.
followers and a realist. So
Has
x
to put in a y.
I think you could say the for all y right here, right after the implication.
For all y.
Then
realist applying to y
Y realist plus y.
Realist applies to y.
implies
Ly.
or x does not like y, so not
Implies
x likes
not x likes y.
That one, yeah.
Let's make that a square bracket.
Is that right?
For all x, if it's a follower of Occam, then for any y, if it's a realist, x does not like y.
y. Right?
I like it.
We did this last time.
Yeah, we did. Oh,
A similar one with the Aristotle
I'm
one.
saying we had this a similar line. Similar line.
Yeah, last time we had the for all x and for all y over here,
Yeah.
and a lot of conversation about how we think it's the same. Okay, this was a premise, and just spin upon itself. Okay, what's our next line?
Any of Occam's followers like at least one of Hobbes' followers. It's going to be similarly structured, maybe.
Any of Occam's followers like at least one of Hobbes' followers.
Oh, for all x,
All.
O applies to x.
For all x, if O applies to x, then
There exists a y.
yeah, let's put a square bracket here. Implies that there exists a y such that
H applies to y and
being a Hobbes follower applies to y.
Usually like
x,
at least.
XLY. X likes y.
XLY.
Are we not gonna look at least one of?
Hobbes
At least one is
Which
the same
one?
thing as saying
Any
that.
of Occam's followers like at least one of Hobbes' followers. There exists is the same thing as at least one.
Yeah.
If there exists a prime number, that means at least one number is prime.
I see that.
Good? I think it's good. Anything you don't like about it? On to the next one. Alright, on to the next one. Occam does have followers.
So there exists X, OX.
3. There exists some X such that they're a follower of Occam. Lucky guy. Therefore, some of Hobbes' followers are not realists. Let's write what we're trying to prove over here.
There exists X such that H applies to X implies not R applies to X.
Yeah. There exists something such that if it were a follower of Hobbes, then it wouldn't be a realist.
Yeah.
Yeah, what?
Is that the same thing as saying some of Hobbes' followers aren't realists?
Yeah.
Let's imagine our domain is any physical object in the universe.
If they're a follower of Hobbes,
If this marker were a follower of Hobbes, it would not be a realist.
I'm not saying there exists a marker or a.
There is. It's right here. This is a thing that exists such that if it were a follower of Hobbes, it would not be a realist.
Okay, I see what you're saying.
So you
So
want
you
to change
need
it to
an
an
and. And it's not.
And there exists something that is a follower of Hobbes,
Yeah.
and it's not a realist. There's actually something out there that follows Hobbes.
Oh, that's weird.
Yeah. We need an actual follower of Hobbes. This marker is not a follower of Hobbes.
But if it
Probably.
was-
You're smart enough, Tim. Not a big fan of Hobbes. Okay, that's what we're trying to prove. All right. So what should we do first?
What to do first? You're gonna want to specify on probably all of those.
Yeah.
Yeah, my gut is always to just do the existential specification first.
Yeah.
Just my gut. No good argument for it.
Doesn't really matter either way.
So we'll say beta is Occam's follower. Okay, so we got our beta. This is universal, not universal. My hand's gonna be all black by the end of class. I did that way too much. Existential specification on line 3. Okay, we're dependent on 3. Yay. Alright. So now, universal specification on this and on this. Replacing our x with beta.
And then are you going to want to specify again
Yeah, would you not?
on the inside terms? Your for all y and for all, or this.
Let me just write it and then try and understand your question.
Okay.
So universal specification on this, replacing the x's with betas. So that means that implies for all y, being a realist applying to y implies not beta likes y. 6.
What?
The second one is that there exists y.
Yeah.
Did I?
The second one.
Thank you. I'll get it, right?
So do you want to specify it on the y, is what I'm saying? Or is that not necessary?
Well, now we can conclude this and this. We have
Yeah.
O applies to beta there. We know if O applies to beta, then we can get this. And we know if O applies to beta, we can get this.
Yeah.
So then we can get these two things.
Yeah.
And we can,
You can and them if you want it.
so I'm going to do 2 and 1 go on 6. Follow me here. I'm going to say this and this tells me this, and I'm going to existentially specify at the same time and replace my y with an alpha. So that tells me that alpha is a follower of Hobbes implies beta likes. Did I really let you guys say that? This should have been an and, right?
Yeah.
Every follower of Occam likes a follower of Hobbes, right? Is that what it said?
Likes at least one of Hobbes' followers.
Likes at least one of Hobbes' followers. So there has to be someone out there that's a follower of Hobbes that we like. So this should have been an and.
Yeah.
Can't believe I missed that.
Same mistake we made before.
So we know that alpha is a follower of Hobbes and beta likes alpha, right? Let's try out our rules here really quick before we get too far ahead of ourselves. This was universal specification, not universal.
Yes.
Yes, universal. Universal specification on line 1.
No.
So I'm choosing 1. This was universal specification on line 2. Choosing 2. This was tautologically implied
And universal
Five and
specifications.
from 4 and
6.
6.
4 and 6.
4 and 6, with a little bit of universal or existential generalization, existential specification in there as well. A few things going on there. Okay. And now, this line though is dependent upon premises 1 and 2.
3 and
3 and 2. So 2 and 3, thank you. Okay, so now we got to there.
Okay, so sorry, I'm just trying to read this, make sure I have it.
So we know, we already found someone. The guy goes by the name of Alpha.
Okay.
Alpha is a follower of Hobbes, and we know Beta likes Alpha.
Gotcha.
Isn't it, the implication supposed to be an and instead of?
Yes. And I read this as an and because I knew that.
Yep.
So both those things are true. Okay. So now, combining this and this, and we're going to universally specify y to be alpha.
Can you specify them to be the same thing?
Yeah, if it's true for everything, it's true for alpha.
Oh, yeah.
Alpha is just one of those things.
Gotcha.
So yes, that is a valid thing to do. So I also know from here that being a realist, if alpha is a realist, then I know it's the case that beta does not like alpha. If alpha were a realist, beta would not like it. How do I know that? Because beta is one of Occam's followers, and therefore they don't like anyone that's a realist.
And then you universe or existentially generalize? No?
So this was tautologically entailed
One more step.
by lines 4 and 6. And we also did some universal specification at the same time. And so now this was dependent. 4 and 6 are dependent on premises. Oh, not 4 and 6.
4 and 5?
4 and 5. Thank you. This is 4 and 5. So this line is using premises 1 and 3. Okay, there we go. All right, now what?
You do the contrapositive of 8?
Right. The contrapositive of 8 would be beta likes alpha implies not being a realist applies to alpha.
And we know that beta likes
And we know beta likes alpha. So this and this gives me alpha is not a realist.
Yep.
So 9 down here, I can conclude alpha is Hobbes and not being a realist applies to alpha.
Uh-huh.
This was tautologically entailed by 7 and 8. And now we're dependent on all of our premises, 1, 2, and 3. Using all the information we were given.
And now you can generalize.
Eugene square box.
Now we can existentially generalize, and then
we're done.
we're done. So then we could say, then there exists y such that being a follower of Hobbes applies to y, and not being a realist applies to y. That was existential generalization on line 9, and we're dependent upon premises 1, 2, and 3. Good. I think I like it. You like it? All right. Let's do one that's a little bit more involved. For every x and y, if x precedes y, then y does not precede x. Let's encode these in premises as we go.
That's a good idea.
So 1. For every x and y, if x precedes y, then y does not precede x.
For all x and y.
Yeah, for all x, for all y.
For all x and y. By the way, I'm going to start writing that rather than for all x, parentheses for all.
Yep.
This is the exact same thing as this.
Okay.
But I'm sick of doing that. Alright, so for all x and y, then what?
Then x py implies
X precedes y implies
not y px.
not y p x.
True.
And hopefully it makes sense to us.
Yeah.
If x precedes y, y can't precede x. Alright, next sentence. We put a big dot where we finished. For every x, y, and z, if x precedes y and y precedes z, then x precedes z. Or in other words, precedes is transitive.
Right.
All x, y, z, x.
For all x, y, z,
X precedes y
if x precedes y
and y precedes
and y precedes z,
That whole thing implies x precedes.
x precedes z.
Seems way easier.
Yeah, this is one of those ones where once you get it into this form, it's a lot easier to understand what it's saying than reading the sentences. Alright. For every x and y, if x precedes y, then x is not equal to y.
All x and y.
So for all x, y, if x precedes y, then
Not x equals y.
we'll just use the not equals to y like that.
We could just be using the less than sign.
Precedes, yeah. Less than
X is less than y. X precedes y.
Okay. We just finished. We're right here.
Right there, yeah.
For every x, y, and z, if y is between x and z, then either x precedes y and y precedes z, or z precedes y and y precedes x.
Okay.
Let's make sense of this.
No.
For every x, y, and z. So here's my x, here's my y, here's my z. For every x, y, and z. If y is between x and z, then you either have x precedes y and y precedes z, or the other way we could have had y between x and z is a picture like this. Here's z, here's y, here's x. These are the two ways y could have been between x and z. So you either have, if y is between x and z, then x precedes y and y precedes z, or z precedes y and y precedes x.
Yep.
So, putting that in plain English,
In English.
it's a lot more clear than that monstrosity of a sentence. If y is between x and z,
Wait, is there a better way to?
X and z. instead of
Okay,
x.
yeah.
then we know x precedes y and y precedes z, or z precedes y and y precedes x.
You need another parentheses. Maybe.
You understand. You're starting to get used to precedence.
Yeah.
You don't need your parentheses every time you use your plus and your times.
Well, it implies could read for that whole word. It is.
Order of logical operations. Not, and, or implies logical equivalence. That's the order you apply them. So you do your ands and your ors before your nots. I'm okay with you getting confused between the order of these two. Outside of that, you should just know.
Okay.
Okay. We're right here, right?
Yep.
For every x and z, if x is not equal to z, then there exists y such that y is between x and z. If x and z are at the same point, then there must exist something between them.
Did we use this somewhere in row analysis? Sounds real familiar.
You use this in geometry. That's why I'm thinking about this in terms of points on the line.
I don't know if it had to do with denseness or if it was something else, but for like completeness axiom, I remember running into this between thing. There's something similar to this.
We proved that between any two rational numbers, there's an infinite number of rational numbers.
Maybe that's what it was.
And yet, you can find two integers that there's no integers between.
Yeah.
And yet, there's the same many integers as there are rational numbers.
Yeah.
Okay, next line. 5. We were saying for all x and z, if x is not equal to z, then, let's do this, then there exists a y such that y is between x and z. Right? And this one makes sense to everyone's intuition. If I've got 2 points that are separate, there exists a point between them.
Yep.
Okay,
Those are all premises, right?
these are all premises.
Yeah.
Yeah, I'm not going to bother writing all the premises and the rules anymore. We got to eventually start phasing some of these things out, getting closer and closer to informal proof. Next, line.
Therefore.
Oh, we're on the therefore now? All right. Let's write the therefore over here. Down over here out of the way, because we probably need some of the space up there. Therefore,
For all x and z.
for all x and z, if x precedes z,
So x precedes z implies
implies
there exists y
there exists y
such that x p y and y p z.
x p y and y p z. Perfect. If x comes before z, then there must exist some y such that x is before y and y is before z, or some y between them, maintaining that order. Cool. Let's prove it. How are we going to prove this?
Start specifying.
It's an implication. How do you prove an implication?
Assume the antecedent.
Assume the antecedent. That's usually a safe place to start. So I'm going to indent here, and we're just going to remember that we need to get rid of our indent before we generalize.
Right.
And I'm not going to bother writing, oh, that's a flag premise, blah, blah, blah. Okay, so let's assume that x precedes z. If x precedes z, what do we know?
It's not equal to z.
It's not equal to z. That's using number 3.
Yeah.
So then using number 3, 7, we're able to conclude that x is not equal to z.
You can use number 5 for something.
Now we can use number 5. Number 5, that tells us that there must exist some y such that y is between x and z.
Oh, but if you look
Now
at
you can use
4,
number 4. Yep.
Using number 4,
for all
We would
x,
have to-
y, and z.
let's existentially general, or let's
Specify on it.
specify on this. Replace that with a beta. So beta is between x and z. Okay, what's next?
Negative 4.
Next, now we know this one. Now we know from here, since beta is between x and z, we know that either x precedes beta and beta precedes z, or z precedes beta and beta precedes x. So here we know x precedes beta and beta precedes z, or z precedes beta and beta precedes x. right?
Yep.
We already know x precedes z.
We already know x precedes z, which would be entailed by which one of those?
Left.
This.
Yeah.
So this would be a little assumed by way of contradiction that this is true, and then we're going to get that this is false.
Can't we just say that?
Huh?
Can't we just say because it's 6, it's the left one?
Well, if you can see it well enough, I don't know, let's just introduce it by way of contradiction.
I thought the left one was the true one. Why are we trying to prove that it's
Oh.
lead to contradiction?
Sorry.
The right one?
Ooh.
The right one would lead to a
Yeah,
contradiction.
I was going to stand up for a second. Okay. Okay, we know that one of these two things has to be true. This one is going to lead to contradiction, right?
Yes.
So assume by way of contradiction that z precedes beta and beta precedes x. I'll do one more line here, 12. Then we get that z
Precedes x.
precedes x. Coming over here, 13,
Backwards arrows.
double indent, double indent.
Wait a minute.
No, z precedes x gives us that using this one. If x precedes y, then it's not the case that y precedes x. So if z precedes x, then it's not the case that x precedes z.
Can we just
So we
say
know not
because-
x precedes z.
How did we get from 11 to 12 again?
Z.
All right, let's scribble some rules down here as we go.
You could just use number 2.
So starting on 6, how did we get number 6? What line did we come from?
5?
Oh, this was our conditional premise.
That is, yeah.
So 6,
So 6.
that was our premise. 7, where did we get that?
5. 5.
This was tautologically implied by 6
3.
and 3. Okay, that's how we got this one.
And then we did 5.
This one was tautologically implied by
7 and 3.
7 and
5.
It's
this and 5. Okay, so that's how we got this one.
Yeah.
This one we got by existential specification
Yep.
on 8.
And then we used number 4.
This one we got
Tautologically implied by 9 and 4.
this one is tautologically implied by 9 and 4. 4 is this one. Okay, 9
Any
and 4.
specifying there or no?
And yeah, we're specifying, but it's good enough that you can follow the logic here.
Yeah.
Here we introduce a premise by way of contradiction.
So why are we doing that?
Assume by way, oops, we don't do the A.
Oh, never mind. That's
By way of contradiction. So we're saying here's another premise we promise to get rid of. By way of contradiction, assume that this to this is tautologically entailed by,
2.
where's transitivity? Number 2. So this is tautologically entailed by 11 and 2. And then we get to here. This is tautologically entailed by 12 and what?
1.
1. Good. And so 14,
RAA.
we get xpz and not xpz. Contradiction. Where's our contradiction?
Where do you put RAA?
So 15, so we conclude the opposite of this.
Yep.
So that can't be false, so this has to be,
True.
oh, this can't be true, so this has to be false. So we conclude not zp beta or and beta p x. Z precedes beta and beta precedes x. This was reductio ad absurdum. Reductio ad absurdum enables us to get rid of this as a premise. So now we're no longer relying on that premise for our validity. So we get rid of the index. Okay. Now, yeah, combine that with 10. 10 says this has to be true or this has to be true.
We know that's false.
and we know that that one's false. So this one has to be true.
Yeah.
So using 10 and 15, so this is tautologically entailed by 10 and 15, we're able to conclude this one. X precedes beta, and beta precedes z.
So X precedes Z.
X precedes beta, and beta precedes z.
And by
17.
2,
By 2, we get,
Looks like we've gone in a big circle.
yeah.
oh no, now we existentially generalize.
Oh, okay.
So then there exists some y
Like,
such that
yeah.
x precedes y and y precedes z.
And then get rid of conditional proof class.
That's existential generalization, 116. All right, so then 18 is conditional proof. So we just barely showed if this is true, then this is true. So we just barely showed x precedes z implies that there exists y such that x precedes y and y precedes z. And that was conditional proof. And that was for lines 6 to 17. So we got rid of that as a premise. So I got rid of this as a premise, I got rid of this as a premise. Those were the only premises I introduced outside of these things. So now we're only dependent upon these things. And we no longer have a flagged variable because our only flagged variables, we got rid of those flagged variables, x there and z there, from here, and we got rid of them being flagged here to there. So they're no longer flagged.
Okay.
And so we can generalize. So 19, we get for all x, if x precedes z,
For all X and Z, right?
give myself a little bit more space too. So we showed for all x and z, if x precedes z, then there exists a y such that x precedes y and y precedes z. We did it. That's universal generalization on line 18 and square box. Any questions on that?
Will you recap one more time when you cannot generalize because of a flag variable?
You can't universally generalize on a flag variable.
Flag variable. Oh, okay. Never mind. I remember now. Sorry, I just have to remind myself just because I forgot the definitions.
Yeah, that's it. So in other words, we can't just say, what if this were the case, and go from that to, well, then it's always the case.
Yeah.
That's not valid reasoning.
So as long as it's not in the premise, you're good.
If it wasn't a free variable introduced in a premise,
Right.
you're good.
Right.
Okay. That ends that section.
Cool.
Move on now to identity.
I'm gonna watch the rest of it later.
Sure you will. And Peter's going to be at class next week.
He said he would be.
I showed up.
It's funny when he shows up.
He said it's his mom's birthday, so we can't have it.
His mom sure carries out her birthday. This is like the 5th class in a row.
Shoot. Yeah,
See ya. Okay, so now we get to a really cool section because now we're finishing off our rules for logic that we are going to care about. So we just barely finished predicate logic. So first we did propositional logic. On top of that we did predicate logic. Now we're getting to logic with identity, which is built on top of predicate logic.
Oh, wow.
Yeah, 3 layers there. Should I do we'll do the review right at the end, and that would be perfect. And show you how all 3 of them relate to each other. So now logic with identities. Up until now, we've just been treating identity like any other predicate. Identity is a predicate. That takes two terms. It's a relation. Remember, a relation is a predicate that takes two terms. Maybe go back over some basic terminology. What's a proposition?
Something that is T.
That's how I know you're reading rather than thinking.
Because that word is small.
A proposition
True or
is something
false.
that's either true or false, not
Yeah.
both.
It's a
That's a
sentence.
proposition.
Sentence, right? Basically.
Yes, a sentence, the way the author is using sentence, a sentence is a type of proposition.
True or false?
It's something that's true or false. Propositions. When I was talking about alpha or beta, alpha and beta are propositions. Things are true or false. Propositional logic. We're looking at things like that, alpha or beta. With what we call true functional sentential connectives, or what we're also going to call logical operators. That was propositional logic. Predicate logic, we introduced predicates. Okay, what's a predicate? Very different from a proposition.
It's a proposition value function.
That is such a beautiful answer. I couldn't have said it any better myself. It's like you took the words right out of my mouth.
Crazy.
It's something that takes terms and spits out true or false.
Yep.
So is blue is a predicate. All these proofs we were doing, we've been using predicates left and right. Over here we were doing is a horse predicate, is the head of predicate. This is the head of, took two terms, so it's also a relation. Those were all predicates. We've been using a lot of propositions. We've been using a lot of predicates. Okay. Lost what my point was in all that. Oh, equals. Equals is a predicate. It's a predicate that takes two terms. So it's a relation. Special type of predicate called a relation.
Okay.
Up till now, that's how we've been treating equals. And that is exactly how you treat equals in propositional and first order predicate logic is what we've been doing. But some people just say predicate logic. Now that we're getting to logic with identity, we're going to start treating equals different from every other relation.
Why?
Because that's what you do in logic with identity. You no longer treat it just like a relation. You introduce some special rules that have to do with just identity.
But it's still a type of relation.
It's still a type of relation, but now we're going to give it some special rules.
Right.
It's just like up until now, I mean, or, and, not, implies, and logically equivalent. Those are just logical operators. They're just like every other operator, but we treat them special. You start treating them special in propositional logic, which is the first logic, and always treat them special after that. When I create an interpretation of a sentence, I can't replace and with an or, just because they're both logical operators. Nope, can't do that. That's an invalid interpretation. Similarly, with our equals now, when an equals is there, you don't get to replace it with other predicates. When you do an interpretation of equals, you have to leave it as equals. Equals stays equals. Because we're going to create special rules now for equals. So, here on out, we're treating it as a special predicate, and it's going to have its own special rules. And these special rules only work with equals, and they're not true of other predicates. Equals or identity. Same thing. All right, so logic of identities now. Going back to grammar, you were taught your to be verbs. Be, am, is, are, was, were, being, and been. These are the words that we will use to encode identity in the English language. Now, we use these words to encode identity, but just because we used these words does not mean we did encode identity. Every time we encode identity in English, we use these words, but not every time we use these words did we encode identity.
Right.
Let's give examples. I say Charles III is the King of England. What am I saying? I'm saying Charles III is identical with, is equal to, the King of England.
Same thing.
If you can replace, as a general rule, if you can replace your to be verb with, is identical with, then it meant the same thing as identity.
Yeah.
So Charles III is identical with the King of England. They're one and the same thing. Current King of England. James Madison was the fourth POTUS as President of the United States. Common acronym, POTUS. James Madison was the fourth POTUS. What are we saying? We're saying James Madison is identical with the fourth President of the United States.
Okay.
They're one and the same thing. You're talking about one, you're talking about the other. All right. Now I'm going to reuse is and was and have them not mean identity. Snow is white. Am I saying snow and white are identical?
No.
No. I'm saying white is a property snow happens to have. Or I'm saying snow satisfies the is white predicate. I'm not saying snow is identical with white. So you can't just blindly replace is with equal signs and have it work. Similarly, I say George Washington was alive. Is George Washington identical with alive?
Nope.
In our hearts.
Okay.
The answer is no. They're very different things. So, anytime we encode identity in English, we use the to be verbs. But just because we're using the to be verbs does not mean we're encoding identity. Okay. So with identity, we introduce two laws or two principles to our logic. And that's it. Well, it's going to come out in one rule. So here's the two ideas, and then we're going to encode them in one rule, and so we're going to add one more rule on top of our logic. One more rule of derivation. Okay? So first, we introduce the law of identity. What's the law of identity? It says for all x, x is equal to x. The way it's the way it's commonly said is everything is identical with itself. Like if you read it in some philosophical book and they were talking about the law of identity, they say everything is identical with itself. Here's the notation for it. Nice and good. Okay, next we have the principle of existentiality. What does that say? It says if x is equal to y, then something is true of x if and only if it's also true of y. Or the way we often summarize that is equals may be substituted for equals. Those are saying one and the same thing. At first glance it might not seem like that's what they're saying, but that's what it's saying. Equals may be substituted for equals. If x is equal to y, then something is true of x if and only if it's true of y. Equals may be substituted for equals.
Are you saying like x can be substituted for y and stuff like that?
Yeah, that's what it enables us to say.
They have
I
the
thought you were
same
saying,
If
like,
x is equal to
predicate
y,
can be substituted for other equal predicates or something like that.
oh no. So that's why it's just a way that it's commonly said. So here's the way people actually remember these things. They remember everything's identical with itself and equals may be substituted for equals. So these are the two principles that we introduce with identity. And we have a rule that encodes those two principles into one rule. And so it's just that rule that we use from here on out for identity. So here's the two principles, the two concepts. And this one rule is going to encode both of those. So let's jump to the actual rule and then we'll finish my notes here. Jump to the actual rule that we're going to introduce, and it's just this one rule that we introduce for identity. And then that's it for identity logic. Rule I, rule of identity. If x is equal to y, and S is an open formula, why open? We'll get to that. If S is an open formula containing x, then we may derive t, provided that t results from S by replacing x with y. In other words, we can replace x's with y's in our formulas, doesn't change anything.
Right.
Furthermore, we may always conclude x is equal to x. So this furthermore, we may always conclude x is equal to x, gives us the law of identity. The first part told us we can substitute equals for equals.
So that rule I is what we would use. All this other stuff is just like parts of it. Is that what you're saying?
Yeah, this is helping you understand the justification behind rule I.
Did you see
Rule I is telling us we can use these two ideas. We can use the law of identity and we can use the principle of existentiality. That's what rule I says.
You have a note there about second order predicates.
Yeah, I just wanted to jump to this while we had the 2 points and I got it.
Okay.
So you see how rule I is simply saying you can use this and you can use this. That's all it's saying.
What is an open formula?
An open formula, one without the quantifiers, has free variables.
It has to be variables. Why is that an important distinction?
We'll get there.
Okay.
So we'll get to the openness, but first, make some notes. So my first note here is we are now in propositional and first order predicate logic with identity. That's the name of the field we're technically in now. Prior to this, we were in propositional and first order predicate logic before we introduced identity. That's what we were in before. If you go all the way back before we had terms, before we had predicates, before we had quantifiers, all the way back to when it was just predicates, basically just sentences and sentential connectives, that was propositional logic. We just had propositions and logical operators. Sentences and truth functional sentential connectives. Propositions, logical operators. That was propositional logic. Okay, so that's technically the name of the field that we're now in. Note. So we said first order predicates. Why did we say first order predicates? Well, there's a concept of a second order predicate, a third order predicate, a fourth order predicate. What is all this nonsense? A second order predicate, that's a predicate that takes a predicate as its argument. So it's not a predicate. So right now, the way we think about predicate is you give it a term and it spits out true or false. Second order predicate, it's a predicate that you give it a predicate and it spits out true or false.
But the predicate that you give it has to have terms connected to it?
To be evaluated, no, it's the predicate is the input, and it will spit out true or false.
That notation sounds like it could get pretty confusing.
We never use this in mathematics
Okay.
Why?
Forgot.
because it's not that useful.
Well, is it useful outside of mathematics?
There's fields that they find uses for it. I've never gone through second order predicate logic, so I don't know the associated fields.
It's basically just an extension. Now you're what predicates instead of terms.
I'm guessing that there's just first order predicate logic and then any order predicate logic. Because then you can have the notion of a third order predicate. What's a third order predicate? A predicate that takes the second order predicate as its argument,
Yeah.
etc. And so they have their arguments as to why it's a useful field to study, not useful to math. I'm aware of. Maybe there's some field in math we're used. I don't know. But so there's that idea. That's why we keep saying first order predicate logic. Most people just call it predicate logic rather than specifying first order. Okay. So we'll jump to answering Levi's question real quick. Check on the camera. Can you see my finger?
Yeah.
Can you still see my finger?
No.
Okay, so let me put my squiggly line so I don't accidentally go past it. So let's jump to Levi's question. Why open formulas? Well, if you didn't require it to be an open formula, here's what you could do. We could have x equals y as a premise, and we can have there exists x such that x is not equal to y. So here's two premises. From these, if I allow you to substitute into closed formulas, you could replace now the y with an x and conclude this, which is false. So you'd be able to conclude this from these two things.
Yeah. What? Why?
Why can't you? Because there exists x here is not the same as the x here.
Right.
If you wanted to get this open, you'd have to replace that x with an alpha, and now you could do the substitute that you wanted.
Right. I'm just confused as to how you can have premise 1 and 2 because they are in the same.
It could have showed up in different places in your proof. You introduce x, you say assume x, da 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 da, and maybe somewhere else you introduce this, there exists y, da 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 da. The point is, since you can use the same variables to talk about different things, you don't want to accidentally connect those things. And the thing that forces you to be talking about separate things is our quantifiers, oftentimes.
Right. So you always have to leave those as free variables, is what you're saying.
What we're saying is, when you use an identity, it has to be an open formula. You can't substitute into a closed formula with identity. Otherwise, you're going to break our rules. And we almost never do anyways. Because notice the first thing we do is we get rid of all our quantifiers, then we start working with the thing. And that's when you use identity. Then you put the quantifiers back in. And that's the way it typically goes.
Okay.
Okay, so prove a couple quick theorems of logic now. Not the theorem I promised we'd prove over there, but some theorems. Oh, this is I tried writing it here. And
Do you have to have identity to
Chuck, where do
prove
you want?
that theorem we were talking about? Is that why we waited?
No, you don't need identity to prove the theorem over there.
Okay.
It's just the next section is theorems on logic. I'm going to prove a couple things here that the author doesn't bother proving. He just says, and notice that this appeals to your intuition. I wanted to show explicitly how they follow from these two things. Okay, so first thing I wanted to prove is that for all x and for all y, if x is equal to y, then y is equal to x. Let's prove that. How do you prove an implication? Assume the antecedent, show it implies a conclusion. So assume the antecedent, assume x is equal to y. That's our premise. It only depends upon line 1, and we have the flag variables x, y. Right? Next, I introduce x is equal to x. That is using rule I, the rule of identity. We can always conclude x is equal to x. This is not assuming anything. That's a fancy symbol for the empty set. We get real tired of having to write that and that. Circle with a line through it's a lot easier. That's the same thing as that. It's not dependent upon any premise. I don't have to assume anything's true to know x is equal to x. Okay. So now, use this other part of rule I. So first we were using this right here is using the second part of rule I. Now we use the first part of rule I. Which is, this is an open formula. I know x is equal to y, this is an open formula. Therefore I can replace my x here with a y.
Right.
So that's how I get from here to here. So I got y is equal to x. That's using rule I on lines 1 and 2. Now this line 3 is dependent upon premise 1 for its validity with 5 variables x and y. Sorry, the whiteboard right here just does not take. That's an I with a 1, comma 2. This says y is equal to x. Trying to go over again is doing nothing. Sorry guys. Y is equal to x. We replace the x with the y using rule I. That's an I. Okay, so what did we show? We showed if x is equal to y, then y is equal to x. And we use conditional proof. So we got rid of 1 as a premise. So now we're dependent upon nothing for our validity.
So there are no premises.
There are no premises. That's what it means for it to be a theorem of logic. It doesn't have any premises.
Really?
Yeah.
Didn't know that.
So now we can universally generalize. And we can say for all x and y, if x is equal to y, then y is equal to x. Universally generalized, again, we're dependent upon no premises. No premises means that you can use it now in every single field. Because this is something that didn't depend on any premises. So if your axioms are the axioms of arithmetic, you can still use identity this way. And so every single field of math, it's valid to use identity. Because all math presupposes first order predicate logic with identity. Right? Make sense? So this is something you can use in every field of math. And you do use it in every field of math. I think. I don't know. Should say that. Okay. So that was the first proof. Let's do the next proof. The next proof is proving that for all x, y, and z, if x is equal to y and y is equal to z, then x is equal to z. Make sense?
Mm-hmm.
Okay. Again, it's an implication. Assuming the antecedent shall then implies the conclusion. So I assume x is equal to y and y is equal to z. Right?
Yep.
And now, I know x is equal to y, and I know y is equal to z, so I can substitute in my y with a z there. So I take this and I replace my y with a z. Using the rule of identity. X is equal to z.
That was easy.
That was easy. Now, I showed this implies this, so I get rid of this as a premise. So on this line, I again have no premises. It's not dependent upon anything for its validity. And then universally generalized, and we get this, dependent upon no premises.
Yep.
So this is a rule of logic, or a theorem of logic, I mean.
Mm-hmm.
Cool. Now, what did we just really prove? We just really showed that identity is an equivalence relation.
Oh.
Oh! Yeah, these things never go away. What did we show? We showed identity is reflexive. What does it mean for a relation to be reflexive? It means for all x, x is related to x. Replace your r with equals, and that's what we just really showed. We showed for all x, x is equal to x. Well, we didn't show that one. That was given to us. That was right there. Then we did this. We showed for all x, y, if x is equal to y, y is equal to x. What does it mean for the relation r to be symmetric? It means for all x, y, if x is related to y, y is related to x. Equal satisfies that. And transitivity. We showed for all x, y, and z, if x is related to y and y is related to z, then x is related to z. We show equal satisfied that.
Yep.
So we showed equals was reflexive, symmetric, and transitive. That's what it means to be an equivalent relation. Right? Coming back full circle? Not full circle, but coming back to stuff we already talked about before. Stuff I told you is ubiquitous in math and comes up over and over and over again.
Good.
Relations of functions, you'll never get away from them. Okay. And then this was some dead whiteboard, so I had to start drawing down here.
Just doesn't draw.
It was,
I see.
it's kind of working. Who's been, don't like even here, kind of got good after a bit. All right, next thing we're going to prove is identity of indiscernibles. This is the contrapositive, not the contrapositive. What's the name for the inverse of an implication? The converse. This is just a converse of the principle of existentiality. Principle of existentiality said, if x is equal to y, then something is true of x if and only if it's true of y. This says, if something is true of x if and only if it's true of y, then x is equal to y.
Okay.
So this is the converse of that, and we're going to prove it's true. And doing this formally would require me to define a predicate and get kind of messy, so we're going to do an informal proof of this. So I'm going to show if something is true of x if and only if it's also true of y, then x is equal to y. Assume the antecedent. Assume everything that's true of x is also true of y. Sorry, that's not quite what it says.
Not quite.
Assume something's true of x if and only if it's true of y, is what I meant to say. Assume something's true of x if with two f's, if and only if it is also true of y. All right. So assume our premise, assume our antecedent, I mean. Now observe that x has a property of always being identical with itself. That's from the law of identity. Now we assume that y has every property x has. X has a property of being identical with x. So then y must have the property of being identical with x. How would I formally have proven this? I would have defined some predicate to be is equal to x, and this would be stated formally as for all predicates, if it's true of x, then it's true of y. Observe that this predicate is true of x, therefore it's true of y, and it just would have kind of been a mouthful. But that would have been the formal way of doing it, which I didn't want to do. Okay, and then we already talked about the y open formulas. Any questions on the stuff over here before I move the camera? All right, there we go. Logic with identity. Easy as pie, right? Easy as rule I.
Yeah.
Okay. We can see. Okay, let's do an example of a proof where we use identity now. Be detectives for a second here. See if we can come to any great conclusions. The man who committed the crime was in the apartment. Now, if anyone was in the apartment, he was in town. And if anyone was in Mexico, he was not in town. Barnes was in Mexico. Therefore, Barnes did not commit the crime.
Yeah. Yeah.
That's why mathematicians are not.
I'm not sure if Sherlock got this right. Let's check it. Doesn't seem pretty obvious.
It seems pretty obvious.
All right, let's see if we can prove it then.
Okay.
1. What's our first line?
There exists an x, or
No, let's not do that.
you just say that a applies to x.
What terms do we have?
You have a man who was in an apartment.
What are the types of terms that we have? We have variables, operators, and
Predicates.
Constant.
constants.
Oh.
The criminal is a constant. That's one and only one person. So we can just start out with being in the apartment applies to the criminal. That is a proposition. We only need quantifiers to turn predicates into propositions when there's variables.
Right. That's true. That's true.
We did constants before we did variables. So you don't always need the there exists or for all to make sure it's a proposition.
Okay.
Does that make sense?
So that says.
Okay, so
Anyway.
the criminal was in the apartment.
Yeah.
Okay.
That's one. Okay, what's line 2? Now, if anyone was in the apartment, he was not in
For
town.
all x, ax implies
For all x, being in the apartment applying to x implies what?
tx or neighboring.
Implies in town applies to x.
Yeah.
Okay, now what?
For all x.
For all x.
mx implies not tx.
Being in Mexico implies not tx.
And then
These
you
are all
have
premises.
another constant called Barnes.
And
And you
applies
say
B.
MB, yeah.
And 4 is being in Mexico
My bad.
applies to Barnes. Barnes was in Mexico.
Whoa.
Very good. So then you would specify on, you universally specify on 3. Or maybe you just apply it, you say MB implies not TB.
Yeah, not TB.
Are we trying to prove that B does not equal C? Just to clarify.
Therefore, Barnes did not commit the crime? Yes. We're trying to show Barnes and the criminal are not identical. So you're saying, we know M applies to B, and we know M applying to B implies not in town applies to B.
Yeah.
So I'm okay with just skipping straight to, okay, we know that not being in town applies to Barnes.
Yep.
Okay?
And then,
You can use the contrapositive of 2.
yeah.
The contrapositive of this. It says, if you're in the apartment, you are in town. The contrapositive of that is if you're not in town, then you're not in the apartment.
So
We know Barnes was not in town, so we can conclude Barnes is not in the
Apartment.
apartment.
Yep.
Not in the apartment applies to Barnes. Okay, now what?
Did you say alibi?
Well, you have that, whatever it was called, where every property that applies to B would have to apply to something identical with it.
Here is our only rule that we can use.
Oh, it's easy.
This is our only actual rule of derivation.
Okay.
I was showing that from these rules we can conclude these other things.
Okay.
But this is our only rule that we get to use outside of our other rules that we already have.
We can assume B is equal to C and.
And
There you go. Assume by way of contradiction.
okay.
So let's really quick finish these here. This was tautologically implied by 4 and which one? Was that 3? Yep. And this one, I wrote that so low. No, I didn't. By 4 and 3. And this one was tautologically implied by 5 and 2. So
Great.
here our premises were
4 and 3.
3, 4. Yeah. And this goes to this. It keeps tripping my eyes for some reason. Too close.
3, 4, 2.
And then this one is using this one,
2, 3, 4.
2, 3, 4. So we've used everything except for the fact that the criminal was in the apartment. Okay.
So it's easy.
So 7. What are we going to assume by way of contradiction?
That B equals C.
Yeah, we're going to assume that Barnes is the criminal. Let's assume Barnes is the criminal. And this is a premise. I'm going to start saying, by way of contradiction, and that means it's a premise that we promise we're going to get rid of later. Okay, so assume by way of contradiction B is equal to C. And then what do we get?
And you get AB.
AB equals AC.
Then we get AB from this line and this line, using our rule of identity with line 1.
So you get
So then we
AB
get-
and not AB.
Being in the apartment applies to B. That's using identity on 1 and 7. So then we get 9, AB, and not AB.
Contradiction.
Contradiction. Therefore,
Use the length of C.
10, we get B is not equal to C. That was by reductio ad absurdum. And we're done. And we introduced that as a premise, we got rid of it as a premise, and so now our premises are 1, 2, 3, and 4. Good?
Good.
Alright. Interpretations with identity, I already said this, but I'll say it again. Interpretations with identity. We cannot substitute equals with any other predicate. In any interpretation, you always have to keep equals equals. Example. if I know that for all x and for all y, x circle y is equal to y circle x, and if I create an interpretation for that as for all x, y, x plus y is less than or equal to y plus x, that was invalid. It's true, but it's invalid. That's an invalid interpretation if we're in identity.
You're saying less than.
If we were just in propositional and first order predicate logic, this is a valid interpretation of this.
Okay.
But since we're not now, since we're in logic with identity, we can no longer take that and replace it with that. That used to be something we could do. We can no longer do that as an interpretation.
That's good. But less than or equal to is could also be equal to, like that's an option, right?
It's a different predicate. You're just thinking, well, since what we actually call that is less than or equal to, then this predicate is a disjunction of these two predicates.
Yeah.
But no, you can just define it explicitly, and it just happens to have a really long name. We could have just easily called that the Frank operator, or the Frank predicate.
Okay.
So it's just a name that's making your intuition think that.
That's an illegal move. That's what you're saying.
This to this was a legal interpretation before identity. Now, this to this is an illegal interpretation with identity.
Okay.
Forget whether it's a true interpretation or a false interpretation. It's not even an interpretation anymore. You have to preserve identity. We now treat equals similar to how we were always treating sentential connectives. It would have been invalid for me to go from, for all x and y, xq, y, or yq, x, to, for all x, y, x is less than y, and y is less than x. No, I can't just replace an or with an and when I do an interpretation. Or maybe replace a or with a not. Maybe that's saying this or with an implies. I can't replace an or with an implies when I do an interpretation. Always and forever throughout this class, when we did interpretation, we kept our sentential connectives, our logical operators. Now in logic, you treat equals the same way. You always replace it with its own symbol. Okay, over stressing it. Do you get it? Okay, and then something I told you I'd give you the definition for. Here it is. So now we have identity, we can define this quantifier. This is, there exists a unique x, or there exists one and only one x. So how do we define that? There exists one and only one x such that p of x is true. That means, this is how we're defining it. Everyone used to that colon in a definition. You're saying this is logically equivalent to this thing, and the colon is on the side of the new thing I'm defining. So I'm defining it in terms of things we already know. Terminology, this is called the definiendum, and these are called the definiends. Definiends are the symbols you already know. The definiendum is the new symbol you're defining. Anyways, so how do we define it? We define that to mean that there exists an x such that p of x is true, and for all y's, if p happens to be true of y, then y must have been identical with x, because x is the only thing it's true for. So there exists an x such that p of x is true, and for any y out there, if p was also true of y, then y was really the same thing as x.
Makes sense.
Good?
Mm-hmm.
So there's the exact definition of that operator, since I can't remember who asked about it, but there it is. Okay, so now high level view of everything we covered of logic. First we covered propositional logic. Propositional logic, all we had were propositions. What are propositions? They're things that are either true, XOR false. That's an XOR.
Oh, that's what I get.
XOR means one and only one of them is true. Exclusive OR, yeah. So proposition, something that's true or false, not both. And then our logical operators, or our truth functional sentential connectives, were not, and, ors, implies, equivalents. These were the only two things we use in propositional logic.
And the roles.
And the rules, but I'm saying the only symbols we used. When I wrote something on the board, it was either a proposition or it was a logical operator, except for parentheses. I guess we're also parentheses.
Okay.
The rules we were able to use in propositional logic were rule P, that said we could introduce a premise at any point. Rule T, which says if a line is tautologically implied by previous lines, then we can put it there. Rule T is the one that basically tells us we can use what are called our rules of logic. These are our rules of derivation. We need to be careful to keep those separate. What's a rule of logic? It's something that shows a tautology. That's a rule of logic says not alpha and beta is not alpha or not beta. That's a rule of logic. So rule T basically says we can use our rules of logic. And then rule CP was our rule of conditional proof. You can introduce something as a hypothetical premise and then get rid of it later, saying it's an implication. If you show your premises and alpha implies beta, then your premises implies alpha implies beta. Those were the only rules we were able to use in propositional logic. We derived reductio ad absurdum. That was also one that we used here. But reductio ad absurdum is just using these three rules to prove it. So it wasn't a foundational rule in and of itself. So these were our only three foundational rules, and all the symbols we wrote were either propositions or logical operators and parentheses. And we would prove things like this thing. Here's one of the things that we proved way back when. We showed that if A implies B or C, and B implies not A, and D implies not C, then A implies not D. That's going back to one of our old proofs. These were the kinds of things we proved in propositional logic. Everything there is either a proposition, something that's true or false, or it's a logical operator, and parentheses. Then we moved on to predicate logic. Predicate logic, we introduced predicates. What's a predicate? It's a proposition valued function. You give it a term, and it spits out true or false. Is white is a predicate that takes one term. Likes is a predicate that takes two terms. Predicates in and of themselves are not true or false. You got to give them a term to make them true or false. Is white is not true. If I give it this snowflake or this chalk, then it spits out true. If I give it this eraser, it spits out false. The is white predicate. Right? That's one way we can make a predicate true or false. The other way we can make a predicate true or false is we give it a quantifier. I can't say whiteness. Whiteness applies to X, true or false. I can't say that. But I could say, for all X, whiteness applies to it. Everything is white. Okay, now that's true or false. Or I could have said there exists X such that whiteness applies to it. That's also true or false. There exists something that's white. That's also true or false. White being the predicate there. So we introduce predicates. Proposition value functions. You give it terms and it spits out true or false. We introduce terms. We had constants, variables, or operators that we use to combine constants and variables however we want. 2 plus 7 is a term. It's a combination of two constants with an operator. X plus 4 is a term. It's a variable, an operator, and a constant all together. Those were terms. And then we introduce our quantifiers for all and there exists. And we introduce 4 new rules. Universal specification, universal generalization, existential specification, and existential generalization. And that ended propositional and predicate logic. Notice predicate logic has to be built on top of propositional logic. Doesn't make sense to talk about this in a vacuum outside of this. Always has to be built on top of it. And then we built on top of that logic with identity, which introduces just rule I.
That's it.
Rules.
Rules I. Because I rules. Yeah. And so that's big picture of all the logic that we're doing. After this, we'll be proving some theorems of logic. So some things that you can use in any field. Things are always true when you're using logic. And then we'll get to theory of definition. And then with that, we're ready to jump into axiomatic systems. Because we already know 3 of the 4 components of every axiomatic system. Every axiomatic system, it has its undefined terms, it has its axioms, it has its theorems, and then it has its definitions. And so all we need now is to know how to do definitions, and we're ready. Because everything up till now has been basically, how do you prove theorems?
How long will it take to do definitions?
I don't know, a couple classes. So next time, we'll do, logical theorems, and then we're going to do a deep dive into arithmetic. And then after that, we'll move to definitions. So I'm not sure how long that'll take.